Right now, you are sitting somewhere safe, maybe in a chair, maybe in bed. The walls around you are solid. The air is still. Everything feels permanent, stable, real. The laws of physics that govern your world have been the same since before you were born, and they will be the same tomorrow. Atoms hold together. Light travels at its constant speed. Gravity pulls you gently toward the Earth. Everything is as it should be. But what if I told you that everything you know, everything that exists, could end in an instant? Not from some external threat, like an asteroid or a supernova. Not even from a black hole swallowing the galaxy. What if the universe itself is fundamentally unstable? What if the very fabric of reality, the quantum fields that make up empty space, could suddenly shift to a different state, rewriting the laws of physics as it goes, traveling outward at the speed of light, erasing everything in its path? This is not science fiction. This is a genuine possibility discussed by some of the world's leading physicists. It is called vacuum decay, and it might be the most quietly terrifying concept in all of modern science. Before you close this window and go back to feeling safe, let me be clear. This is not about fear. This is about wonder, about the profound strangeness of the universe we inhabit. Because when you really understand vacuum decay, when you grasp what it means for reality itself to be metastable, you begin to see the cosmos in an entirely different light. If you find this intriguing, if you want to explore the deepest mysteries of existence with me, consider liking this video and subscribing. There is so much more to discover together. Now, let us begin at the beginning. Not with vacuum decay, not yet. First, we need to talk about something simpler, something you have heard about your entire life, but perhaps never truly understood. We need to talk about empty space. Part 1. The quantum vacuum and the nature of empty space. What is a vacuum? If I asked you to define it right now, you might say it is a place with nothing in it, a region of space devoid of matter, devoid of air, devoid of anything at all. And for most of human history, that is exactly what people thought. Ancient Greek philosophers debated whether a true vacuum could even exist. Some believed that nature abhorred a vacuum, that empty space was impossible, that something always filled the void. Others argued that atoms moved through the void, through true nothingness. The debate raged for centuries. When scientists finally created laboratory vacuums, pumping the air out of sealed chambers, they seemed to confirm that yes, you could have empty space. A place with nothing in it, a void. But they were wrong. In the early 20th century, as physicists developed quantum mechanics and began to probe the nature of reality at its smaller scales, they discovered something profoundly strange. Empty space is not empty. The vacuum is not a void. It is a roiling, bubbling, seething ocean of quantum fields. Let me explain what that means. Everything in the universe, every particle, every force, every interaction, is made of fields, not solid objects floating in space, but excitations in quantum fields that permeate all of reality. The electromagnetic field gives us photons, particles of light. The electron field gives us electrons. The quark fields give us the building blocks of protons and neutrons. Even empty space, even a perfect vacuum, is filled with these fields. They are everywhere, always, unavoidable. And these fields are not static. They are not calm. Even at their lowest energy state, even when no particles exist, quantum fields fluctuate. They vibrate with what physicists call zero-point energy. Particles pop in and out of existence for infinitesimal fractions of a second, borrowing energy from the vacuum itself, then disappearing before the universe notices. These are called virtual particles, and they are real in the sense that they have measurable effects. They influence the behavior of atoms. They alter the properties of light. This is not speculation. This is confirmed by experiment. The Casimir effect, for instance, shows that two metal plates placed very close together in a vacuum will attract each other, pushed together by the pressure of virtual particles in the quantum fields surrounding them. The vacuum, the so-called empty space, exerts force. So when we talk about a vacuum, we are not talking about nothingness. We are talking about space at its ground state, its lowest energy configuration. All the quantum fields exist there, humming quietly with their zero-point energy, but no real particles, no excitations, no matter. Or so we thought. Because here is where things get interesting. Here is where physicists began to realize that the vacuum, this supposedly stable ground state, might not be stable at all. To understand why, we need to think about energy. Let us delve deeper into what physicists mean when they talk about the quantum vacuum. This is worth exploring in detail because it fundamentally challenges our intuition about reality. In classical physics, a vacuum was simple. It was the absence of matter. Remove all the air from a container, and you have a vacuum. Remove all particles, all atoms, all molecules, and you have perfect emptiness. Nothing. But quantum mechanics changed everything. In quantum field theory, the framework that describes particles and forces at the smallest scales, there is no such thing as true emptiness. Every point in space, every cubic centimeter of the universe is filled with quantum fields. These fields are fundamental. They are not made of anything more basic. They simply exist. The electromagnetic field exists everywhere. So does the electron field, the quark fields, the Higgs field, the gravitational field, all of them overlapping, occupying the same space, each vibrating with its own characteristic frequency. And these fields have energy even when they are at their lowest state, their ground state. This is not optional. It is a consequence of the uncertainty principle, one of the foundational principles of quantum mechanics. The uncertainty principle states that you cannot know both the position and momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. This is not a limitation of measurement. It is a fundamental property of reality. Applied to fields, the uncertainty principle means that a field cannot be perfectly still. It cannot have exactly zero energy. There must always be fluctuations, vibrations, uncertainty. These fluctuations manifest as virtual particles, particle-antiparticle pairs that pop into existence for incredibly brief moments, then annihilate. An electron and a positron appear from nothing, exist for a tiny fraction of a second, then disappear. A photon materializes, then vanishes. These virtual particles borrow energy from the vacuum itself, permitted by quantum mechanics as long as they pay it back quickly enough that the universe does not notice. This might sound like mathematical fiction, but it is not. Virtual particles have real, measurable effects. They alter the energy levels of atoms in ways that can be detected with extraordinary precision. They affect how light propagates through space. They create forces between objects. The Casimir effect is perhaps the most striking demonstration. Place two uncharged metal plates very close together in a vacuum. Classical physics predicts nothing should happen, but quantum mechanics predicts that the plates will attract each other, pulled together by the pressure of virtual particles. Why? Because the space between the plates is so narrow that only virtual particles with certain wavelengths can exist there. Outside the plates, in the wider expanse of space, virtual particles of all wavelengths can exist. This creates a difference in pressure. More virtual particles push on the outside of the plates than push on the inside, and so the plates attract. This has been measured. The effect is real. Virtual particles are real in the sense that they have real consequences. So when we talk about a vacuum, we are not talking about nothingness. We are talking about a seething ocean of quantum fields and virtual particles, a complex dynamic system that only appears empty because we cannot see the fluctuations directly. And this is the vacuum that might be metastable. This is the foundation of reality that could, in principle, transition to a different state. Part 2. The Higgs field, energy states, and the false vacuum. Imagine a ball resting at the bottom of a valley. It sits there, perfectly still, perfectly stable. If you nudge it slightly, it rolls back to the center. This is what physicists call a stable equilibrium. The ball is at the lowest point in its landscape. It has nowhere lower to go. Now imagine a different scenario. A ball is resting in a shallow dip on the side of a hill. It looks stable. It is not rolling. But this is not the lowest point. There is a much deeper valley farther down the slope. The ball is in what physicists call a metastable state. It appears stable, it can remain there for a very long time, but it is not truly in the lowest energy configuration. Given the right nudge, the right fluctuation, it could roll down to the true bottom. This analogy is crucial to understanding vacuum decay. Quantum fields, like that ball, have energy. The amount of energy depends on the state of the field. Different configurations of the field have different energies. And just like that ball in the landscape, quantum fields seek the lowest energy state. That is where they are most stable. The vacuum, remember, is supposed to be the lowest energy state, the ground state, the bottom of the valley. But what if it is not? What if the vacuum we inhabit, the configuration of quantum fields that makes up empty space in our universe, is actually a metastable state, a false vacuum? What if there is a lower energy state, a true vacuum, deeper down in the energy landscape? And what if, through some quantum fluctuation, some random chance event, the fields in our universe could transition to that lower state? This is the essence of vacuum decay, and the implications are staggering. To grasp the idea of a false vacuum, we need to understand the Higgs field. You may have heard of the Higgs boson, discovered at the Large Hadron Collider in 2012. The Higgs boson is an excitation in the Higgs field, a quantum field that permeates all of space. The Higgs field is special because it gives mass to other particles. Electrons, quarks, and other fundamental particles acquire their mass by interacting with the Higgs field. Without it, they would be massless, and the universe as we know it could not exist. The Higgs field has a value, an intensity, even in empty space. This is unusual. Most quantum fields have a value of 0 in their ground state. But the Higgs field has a non-zero vacuum expectation value. It is always turned on, even in a perfect vacuum. Now, the Higgs field has a potential energy curve. Think of it like the landscape we discussed earlier. But instead of physical hills and valleys, this is a mathematical landscape describing the energy of the field at different values. And here is the critical question. Is the value of the Higgs field in our universe at the absolute minimum of that potential energy curve? Or is it in a local minimum, a false vacuum? Based on current measurements of the Higgs boson mass and the top quark mass, physicists have calculated the shape of the Higgs potential. And the results are unsettling. The calculations suggest that the Higgs field in our universe might not be in the absolute lowest energy state. It might be in a metastable configuration. Think back to the ball on the hillside. Our universe, with its current Higgs field value, is like that ball resting in a shallow dip. It looks stable. It has been stable for nearly 14 billion years. But there is a much deeper valley in the energy landscape, a true vacuum. And if the Higgs field were to transition to that lower energy state, everything would change. Everything. The Higgs field deserves special attention because it is central to the question of vacuum stability. Let me explain it more thoroughly. Most quantum fields have a vacuum expectation value of 0. That means, in their ground state, when no particles are present, the field itself has 0 intensity. It is there, but it is turned off, so to speak. The Higgs field is different. It has a non-zero vacuum expectation value. Even in empty space, even when no Higgs bosons are present, the Higgs field has an intensity of about 246 gigaelectron volts. This is not a small number. It is a fundamental property of our universe. Why does this matter? Because particles acquire mass by interacting with the Higgs field. The stronger the interaction, the more mass the particle has. Electrons interact weakly with the Higgs field, so they have a small mass. Top quarks interact strongly, so they have a large mass. Photons do not interact with the Higgs field at all, so they are massless. This mechanism, called the Higgs mechanism, is how the universe generates mass. Without the Higgs field, electrons, quarks, and other particles would be massless. They would travel at the speed of light, unable to bind together into atoms. Chemistry would not exist. Complexity would not be possible. The universe would be a very different place. Now, the Higgs field, like all quantum fields, has a potential energy. This potential describes how the energy of the field changes as its intensity changes, and the shape of this potential is critical. Imagine a graph. The horizontal axis represents the intensity of the Higgs field. The vertical axis represents the potential energy. The shape of this graph determines the behavior of the field. In our universe, the Higgs field sits at an intensity of about 246 gigaelectron volts. This corresponds to a minimum in the potential energy curve. The field has settled there because it is a stable or metastable equilibrium. But here is the question. Is this the absolute minimum? Or is there a deeper minimum at a different field intensity? Calculations based on the measured mass of the Higgs boson and the top quark suggest that at very high field intensities, far higher than the current value, the potential energy curve dips down. It develops a second minimum, much deeper than the first. This means the Higgs field in our universe is in a local minimum, not the global minimum. It is like a ball in a valley, but not the deepest valley. It is metastable. Now, why has the field not already transitioned to the deeper minimum? Because there is an energy barrier separating the two minima. To transition, the field would have to climb over a hill in the potential energy curve, and it does not have enough energy to do that. But quantum mechanics offers another possibility: quantum tunneling. The field could tunnel through the barrier, jumping from the false vacuum to the true vacuum, without ever having enough energy to climb over the hill. This is possible, but extraordinarily unlikely. The barrier is enormous, corresponding to energies near the Planck scale. Tunneling through such a barrier is a rare event, so rare that it might not happen for timescales far longer than the current age of the universe. But it is not impossible, and that is what makes vacuum decay a real, if remote, possibility. The top quark plays a crucial role in determining the stability of the Higgs potential. The top quark is the heaviest known fundamental particle. It has a mass of about 173 gigaelectron volts, which is roughly the mass of a gold atom, but concentrated into a single elementary particle. This is extraordinarily heavy for a fundamental particle. The top quark interacts very strongly with the Higgs field. In fact, its interaction is so strong that it significantly affects the shape of the Higgs potential at high energies. Here is how it works. Quantum fields do not exist in isolation. They interact with each other. Virtual particles from one field can affect the behavior of another field. These interactions are described mathematically using a framework called renormalization group equations. When physicists calculate how the Higgs potential changes at higher and higher energies, they find that the top quark interaction drives the potential downward at very high field intensities. The strong coupling between the top quark and the Higgs field creates a negative contribution to the potential energy. If the top quark were lighter, this effect would be weaker, and the Higgs potential might remain positive at all energies, indicating a stable vacuum. If the top quark were heavier, the effect would be stronger, and the vacuum might be unstable, decaying rapidly. But the top quark has just the right mass to make the vacuum metastable. Not stable, not unstable, but balanced on the edge. This is remarkable. A tiny change in the top quark mass, just a few giga-electron volts, could shift the vacuum from stable to unstable, or vice versa. The universe we inhabit is incredibly sensitive to the properties of fundamental particles. And this sensitivity raises deep questions. Why does the top quark have the mass it does? Why is the universe metastable rather than stable or unstable? Is this a coincidence? Or is there a deeper explanation? Some physicists invoke the anthropic principle, arguing that we exist in a universe with these particular properties because they allow for complexity and life. Others search for new physics, new particles or forces that might explain why the constants of nature have the values they do. But as of now, we do not have a complete answer. We only have measurements and calculations that suggest the vacuum is metastable, poised in a delicate balance. Part 3. Quantum tunneling and the mechanics of vacuum decay. To grasp the idea of a false vacuum, we need to understand the Higgs field. You may have heard of the Higgs boson, discovered at the Large Hadron Collider in 2012. The Higgs boson is an excitation in the Higgs field, a quantum field that permeates all of space. The Higgs field is special because it gives mass to other particles. Electrons, quarks, and other fundamental particles acquire their mass by interacting with the Higgs field. Without it, they would be massless, and the universe as we know it could not exist. The Higgs field has a value, an intensity, even in empty space. This is unusual. Most quantum fields have a value of 0 in their ground state, but the Higgs field has a non-zero vacuum expectation value. It is always turned on, even in a perfect vacuum. Now, the Higgs field has a potential energy curve. Think of it like the landscape we discussed earlier, but instead of physical hills and valleys, this is a mathematical landscape describing the energy of the field at different values. And here is the critical question. Is the value of the Higgs field in our universe at the absolute minimum of that potential energy curve? Or is it in a local minimum, a false vacuum? Based on current measurements of the Higgs boson mass and the top quark mass, physicists have calculated the shape of the Higgs potential, and the results are unsettling. The calculations suggest that the Higgs field in our universe might not be in the absolute lowest energy state. It might be in a metastable configuration. Think back to the ball on the hillside. Our universe, with its current Higgs field value, is like that ball resting in a shallow dip. It looks stable. It has been stable for nearly 14 billion years. But there is a much deeper valley in the energy landscape, a true vacuum. And if the Higgs field were to transition to that lower energy state, everything would change. Everything. But how could such a transition occur? How could the Higgs field, resting comfortably in its false vacuum, suddenly jump to the true vacuum? The answer lies in quantum mechanics, specifically in a phenomenon called quantum tunneling. In classical physics, if you have a ball in a valley, it cannot escape unless you give it enough energy to roll over the hill. But in quantum mechanics, particles do not obey classical rules. They exist as probability waves spread out over space. And there is always a non-zero probability, no matter how small, that a particle can appear on the other side of an energy barrier without ever having climbed over it. This is quantum tunneling. It is how particles pass through barriers that should be impenetrable. Quantum tunneling is not science fiction. It is how radioactive decay works. It is how the sun generates energy through nuclear fusion. It is a fundamental aspect of reality at the quantum level. And it applies to quantum fields, too. Even if the Higgs field is sitting in a false vacuum, even if there is an energy barrier preventing it from rolling down to the true vacuum, quantum mechanics allows for the possibility that the field could tunnel through that barrier spontaneously, without warning. It would not happen everywhere at once. It would start in a single point, a random location in space, at a random moment in time. A tiny bubble of true vacuum, a region where the Higgs field has tunneled to its lower energy state, would appear. And then that bubble would expand. Part 4. The bubble, the speed of light, and the impossible warning. Imagine a single point in space where the Higgs field has spontaneously transitioned to the true vacuum. The field inside this bubble is now at a lower energy state than the false vacuum surrounding it. And because lower energy states are more stable, the bubble does not collapse, it grows. The boundary of the bubble, the interface between true vacuum and false vacuum, is called a domain wall. And this domain wall moves outward, expanding in all directions at very nearly the speed of light. Why the speed of light? Because the domain wall releases energy as it moves. The false vacuum has higher energy than the true vacuum. As the bubble expands, converting false vacuum into true vacuum, that excess energy is released. It drives the expansion. The domain wall accelerates, approaching but never quite reaching the speed of light, limited only by the constraints of special relativity. From the outside, if you could see the bubble approaching, it would look like an expanding sphere, growing relentlessly, swallowing everything in its path. But here is the truly unsettling part. You could not see it approaching. The bubble expands at the speed of light. Light itself, electromagnetic waves, also travels at the speed of light. That means no signal, no warning, no information of any kind could ever outrun the bubble. You would not see it coming. You would not detect it. You would have no indication that anything was wrong until the instant the bubble reached you. And in that instant, everything would change. What happens inside the bubble? What does it mean for the Higgs field to be in a different vacuum state? Remember, the Higgs field gives mass to particles. Electrons, quarks, all the fundamental building blocks of matter, acquire their mass through interactions with the Higgs field. If the Higgs field changes to a different value, the masses of particles change. And if particle masses change, the forces that govern atomic structure change. Chemistry changes. Inside the bubble of true vacuum, the laws of physics are different. Not completely different, perhaps. The equations of quantum field theory still hold. The fundamental forces, electromagnetism, the strong nuclear force, the weak nuclear force, gravity, they all still exist, but their strengths, their interactions, the way they shape matter. All of that could be different. Atoms, as we know them, might not be stable. Protons and neutrons, held together by the strong nuclear force, might not bind in the same way. Electrons might not orbit nuclei at the same energy levels. The very chemistry that makes complex molecules, that makes life, that makes stars and planets, might not work. In the most extreme scenarios, matter itself could not exist in the form we know. Atoms would disintegrate. Structures would collapse into unrecognizable configurations of particles. Everything, from galaxies to cells to individual atoms, would be unmade, but it would not feel like anything, because you are made of atoms. Your brain, your neurons, the electrochemical signals that constitute your thoughts and consciousness. All of that depends on the current laws of physics. If the bubble of true vacuum passed through you, your atoms would reconfigure instantly, faster than any nerve impulse could propagate, faster than any thought could form. There would be no moment of terror, no instant of realization. You would simply cease to exist in any recognizable form, and the bubble would keep expanding forever, converting the entire universe to true vacuum, one light second at a time. Let us pause for a moment and think about the speed of light. In our everyday experience, light is fast, extraordinarily fast. It crosses the distance from the Earth to the Moon in just over 1 second. It travels from the Sun to Earth in about 8 minutes. It seems instantaneous, but on cosmic scales, the speed of light is slow. The nearest star to our Sun is Proxima Centauri, about 4 light-years away. That means light from Proxima Centauri takes 4 years to reach us. The Milky Way galaxy is about 100,000 light-years across. The distance to the Andromeda galaxy, our nearest large neighbor, is about 2.5 million light-years. Now imagine a bubble of true vacuum forming somewhere in our galaxy. It expands at nearly the speed of light. How long would it take to reach Earth? If the bubble formed on the other side of the Milky Way, it would take tens of thousands of years to reach us. If it formed in a neighboring galaxy, millions of years. If it formed in a distant supercluster, billions of years. This gives rise to an odd sort of relief, even if vacuum decay is happening somewhere in the universe right now. Even if a bubble of true vacuum formed a billion years ago in a distant galaxy, it might not reach us for billions more years. The universe is vast. The speed of light is finite. But here is the counterpoint. We would never see it coming. If a bubble formed 1,000 light-years away, we would have 1,000 years until it reached us. But we would not know about it. We could not know. No light, no signal, no messenger of any kind could travel faster than the bubble to warn us. We could look at the stars, we could observe distant galaxies, and everything would appear normal. The stars would shine, galaxies would rotate, everything would seem fine. And then, without warning, the bubble would arrive, moving at the speed of light, and in an instant, it would all be over. This is what makes vacuum decay so profoundly unsettling. It is not the violence, it is not the destruction, it is the inevitability, the silence, the fact that it could be happening right now, racing toward us through the void, and we would have no way of knowing. Let us return to the science. How do physicists know that the Higgs field might be in a false vacuum? What evidence do we have? The answer comes from precision measurements of particle properties combined with theoretical calculations. The Higgs boson, discovered at the Large Hadron Collider, has a mass of about 125 giga-electron volts. Physicists also know the mass of the top quark, the heaviest known fundamental particle, which is about 173 giga-electron volts. These two masses, along with other parameters of the standard model of particle physics, determine the shape of the Higgs potential energy curve. When physicists plug these values into their equations and calculate the Higgs potential, they find something interesting. At low energies, the energies we experience in everyday life, the Higgs field sits in a stable minimum. But at extremely high energies, energies far beyond anything we can create in particle accelerators, the potential curve changes. It develops a second minimum, much deeper than the first. This is the true vacuum, and it sits at energies trillions of times higher than anything we have ever observed. The Higgs field in our universe is in the first minimum, the false vacuum. The barrier separating the false vacuum from the true vacuum is enormous, requiring energies that correspond to the Planck scale, the highest energy scale in physics, where quantum mechanics and gravity merge. This barrier is so high that quantum tunneling through it is extraordinarily unlikely. How unlikely? Physicists estimate that the probability of the Higgs field tunneling to the true vacuum is incredibly small. The lifetime of the false vacuum, the average time before a bubble of true vacuum would spontaneously form somewhere in the observable universe, is far longer than the current age of the universe. We are talking timescales of 10 to the power of 100 years or more. Unimaginably long. But, and this is crucial, the probability is not zero. How do physicists calculate something like this? How do they estimate the lifetime of a false vacuum? The process involves quantum field theory, statistical mechanics, and a great deal of mathematics, but the basic idea is surprisingly intuitive. Think back to the ball in the valley. The ball represents the Higgs field. The valley represents the false vacuum. The hill separating the valley from the deeper, true vacuum represents the energy barrier. In classical physics, the ball would stay in the valley forever, unless you gave it enough energy to roll over the hill. But in quantum mechanics, there is always a probability that the ball will tunnel through the hill to the other side. That probability depends on the height and width of the barrier. A tall, wide barrier makes tunneling very unlikely. A short, narrow barrier makes it more likely. For the Higgs field, the barrier is incredibly tall and wide. It corresponds to energies near the Planck scale, about 10 to the 19th gigaelectron volts, far beyond anything we can probe experimentally. The sheer size of this barrier makes tunneling extraordinarily rare. But the universe is large, and it has existed for a long time, and quantum mechanics is probabilistic. Given enough space and enough time, even extremely unlikely events can occur. Physicists use a mathematical framework called instanton calculus to estimate the tunneling rate. An instantan is a solution to the equations of quantum field theory that describes a tunneling event. By calculating the properties of these instantons, physicists can estimate the probability per unit volume per unit time that a bubble of true vacuum will form. When they do this calculation for the Higgs field, using the measured values of the Higgs and top quark masses, they find that the vacuum is metastable, not unstable, which would mean it decays quickly, not perfectly stable, which would mean it never decays. Metastable, it can last for an extraordinarily long time, far longer than the current age of the universe, but it is not eternal. This is based on our current understanding. The calculations depend on precise measurements of particle masses and other parameters. If those measurements change slightly, if future experiments reveal new physics, the conclusions could change. But as of now, with the data we have, the universe appears to be metastable. If the Higgs field is in a metastable state, if it can tunnel to the true vacuum, what could make it happen? The simple answer is nothing. Vacuum decay, if it occurs, would be a spontaneous quantum fluctuation, a random event with no cause, no trigger, no warning. This is the nature of quantum mechanics. Events happen probabilistically, without deterministic causes. A bubble of true vacuum could form at any moment, anywhere in space, purely by chance. But there are scenarios where the probability could be higher. High-energy events, for instance, might increase the likelihood of vacuum decay. Imagine a region of space where the energy density is extremely high, perhaps near the core of a collapsing star, or during the collision of black holes, or in the first moments after the Big Bang. In these extreme environments, the quantum fields are excited to very high energies. The Higgs field fluctuates wildly, and in those fluctuations, there might be a higher probability of tunneling to the true vacuum. Some physicists have speculated that black holes, with their extreme densities and energies, could be sites where vacuum decay is more likely. Others have suggested that cosmic rays, high-energy particles from space, could trigger decay if they interact in just the right way. But these are speculations. The truth is, we do not know. Vacuum decay, if it happens, would be a quantum event governed by probability, not causation. It could happen in the most extreme environment imaginable, or it could happen in the emptiest void of intergalactic space. There is no way to predict it, and that, perhaps, is the most unsettling aspect of all. There is nothing we could do to prevent it. No technology, no understanding, no action could stop a spontaneous quantum fluctuation from triggering vacuum decay. It is beyond our control, beyond anyone's control. Let us think about the observable universe. The portion of the cosmos we can see, bounded by the distance light has traveled since the Big Bang, is about 93 billion light-years across. Everything beyond that is invisible to us, not because it does not exist, but because light from those regions has not had time to reach us yet. Now, imagine a bubble of true vacuum forming at the edge of the observable universe. It would expand at the speed of light, growing larger and larger, swallowing galaxies, stars, and planets. But we would not see it. The bubble is moving toward us at the speed of light. Light from the bubble is also traveling at the speed of light, in the same direction. The two speeds cancel out. No information from the bubble can reach us faster than the bubble itself. We could observe the universe, looking deeper and deeper into space, and everything would appear fine. Galaxies would shine, stars would burn, everything would seem stable and eternal. And all the while, the bubble could be racing toward us, an unstoppable wall of altered physics, invisible, inevitable. When it finally reached us, it would arrive at the speed of light. One moment, the universe as we know it. The next moment, something utterly different. No transition, no warning, no time to comprehend. This is the strange consequence of relativity. The speed of light is not just the speed of light. It is the speed of causality, the maximum speed at which information can travel. And if vacuum decay occurs, it propagates at that maximum speed. From our perspective, it would be instantaneous and total. Part 5. Cosmic Context, Black Holes, and the Limits of Knowledge. You might be thinking, black holes are terrifying. Supernovae are violent. Gamma ray bursts can sterilize entire regions of space. Why is vacuum decay considered more frightening? The answer is scale and inevitability. A black hole, for all its strangeness, is a localized object. It affects the space around it, bending light, trapping matter, but beyond its event horizon, the universe continues unchanged. If you are far enough away from a black hole, you are safe. The laws of physics remain the same. Atoms are stable. Stars shine. A supernova is a violent explosion, but it is brief. It releases an enormous amount of energy, but then it ends. The shockwave dissipates. The radiation fades. And again, the universe beyond the blast continues as it was. Vacuum decay is different. It is not a localized event. Once a bubble of true vacuum forms, it expands forever. There is no stopping it. There is no outrunning it. It does not dissipate or fade. It grows, consuming the universe piece by piece, rewriting the laws of physics as it goes. And unlike a black hole or a supernova, which you could in principle detect and avoid, vacuum decay gives no warning. It is silent, invisible, moving at the speed of light. By the time you could observe it, it would already be upon you. This is why vacuum decay is, in some sense, the ultimate cosmic threat. Not because it is likely, not because it is imminent, but because if it happens, there is nothing anyone could do. No escape, no defense, no hope. But let us not dwell on fear. Let us instead turn to philosophy, because vacuum decay, for all its strangeness, teaches us something profound about the nature of reality. We live our lives assuming that the world is permanent. The ground beneath our feet feels solid. The sun rises each morning, the stars shine each night. The laws of physics, the forces that govern atoms and molecules, the properties of matter, all of these seem eternal and unchanging, but they are not. The laws of physics, as we understand them, are not fundamental absolutes written into the fabric of existence. They are contingent on the state of quantum fields. The Higgs field, the electromagnetic field, the quark and lepton fields, all of these have particular values in our universe. And those values determine the masses of particles, the strengths of forces, the structure of atoms. Change the fields, and you change the laws. Vacuum decay reveals that the stability we perceive is not guaranteed. It is a consequence of the current state of the universe, a state that is potentially metastable. We exist in a particular configuration of reality, but it is not the only configuration, and it might not be the lowest energy configuration. This is humbling. It suggests that the universe, for all its vastness and age, is more fragile than we imagined. Not fragile in the sense of being easily destroyed, but fragile in the sense that its fundamental nature is contingent, not necessary. And yet, here we are. The universe has existed for nearly 14 billion years. The vacuum has not decayed. The stars still shine. Life has emerged and evolved, and we are here to contemplate these mysteries. Some physicists invoke the anthropic principle to explain the stability of the vacuum. The anthropic principle, in its simplest form, states that the universe must be compatible with the existence of observers. If it were not, we would not be here to observe it. Applied to vacuum decay, the argument goes like this. If the vacuum were unstable, if it had already decayed, the universe would be incompatible with life. Therefore, the fact that we exist implies that the vacuum has not decayed, at least not in our region of space. But this does not mean the vacuum is stable. It only means that it has been stable long enough for us to evolve. The vacuum could still be metastable, poised to decay at any moment, and there would be no contradiction. We exist now because it has not decayed yet. If it decays tomorrow, the anthropic principle offers no comfort. Some interpretations of the anthropic principle go further. They suggest that in an infinite multiverse, with infinite regions of space, all possible vacuum states exist somewhere. Some regions have stable vacuums, some have unstable vacuums that decayed long ago, and some, like ours, have metastable vacuums that have not yet decayed. We find ourselves in a metastable region not because it is special, but because it is the only type of region where observers could exist long enough to ask the question. This is a strange and unsettling way to think about existence. It suggests that the universe is not designed for stability, but that stability is a selection effect, an accident of probability in an infinite cosmos. Is there any way, even in principle, to detect an approaching bubble of true vacuum before it reaches us? The answer, frustratingly, is no. As we have discussed, the bubble expands at the speed of light. Light itself also travels at the speed of light. No signal can outrun the bubble. By the time any information reaches us, the bubble itself would have arrived. But what if we could detect precursor effects? What if the transition to true vacuum created ripples in spacetime, gravitational waves, that propagated ahead of the bubble? Unfortunately, gravitational waves also travel at the speed of light. They obey the same speed limit as light and matter. If the bubble produces gravitational waves, those waves would arrive at the same moment as the bubble itself. What about neutrinos? Neutrinos are nearly massless particles that interact very weakly with matter. They can pass through entire planets without being stopped. Could neutrinos from a vacuum decay event reach us before the bubble? No. Neutrinos also travel at, or very close to, the speed of light. They would provide no advance warning. The laws of relativity are absolute. Nothing can travel faster than light. And because the bubble expands at the speed of light, no signal, no warning, no messenger of any kind can precede it. This means that vacuum decay, if it occurs, would be the ultimate surprise. One moment, business as usual. The next moment, oblivion. No time to react, no time to comprehend. And yet, the fact that we are here, contemplating this possibility, is itself a kind of answer. If vacuum decay had already occurred in our past light cone, the region of spacetime from which light could have reached us, we would not exist. The fact that we do exist means that no bubble of true vacuum has reached us yet. But it tells us nothing about the future. The Planck scale is a fundamental limit in physics. It represents the energy, length, and time scales where quantum mechanics and gravity merge, where our current theories break down and new physics must take over. The Planck energy is about 10 to the 19th giga-electron volts. The Planck length is about 10 to the negative 35 meters. The Planck time is about 10 to the negative 44 seconds. These are incredibly small and incredibly large scales, far beyond anything we can probe experimentally. The Higgs potential The energy landscape that determines whether our vacuum is stable or metastable is sensitive to physics at the Planck scale. If there are new particles, new forces, new interactions at those extreme energies, they could change the shape of the potential. They could stabilize the vacuum, or they could destabilize it further. This is one of the great uncertainties in modern physics. We know the standard model of particle physics works extraordinarily well at the energies we can access. But we also know it is incomplete. It does not include gravity. It does not explain dark matter or dark energy. It does not account for the matter-antimatter asymmetry in the universe. At the Planck scale, something new must happen. Perhaps string theory, perhaps loop quantum gravity, perhaps something we have not yet imagined. And whatever that new physics is, it could change our understanding of vacuum stability. Some theorists have proposed that supersymmetry, a hypothetical symmetry between particles, could stabilize the Higgs potential. Others suggest that extra dimensions of space, curled up at tiny scales, could alter the energy landscape. Still others propose that the vacuum is part of a vast multiverse, with different regions having different vacuum states, and ours happens to be metastable. We do not know, and until we can probe physics at the Planck scale, we will not know. But the uncertainty itself is illuminating. It reminds us that our understanding of the universe is incomplete, that there are mysteries at the deepest levels of reality that we have only begun to explore. Let us take a step back and consider the history of the universe. 14 billion years ago, give or take, the Big Bang occurred. The universe began as an incredibly hot, dense state, filled with energy and radiation. As it expanded, it cooled. Particles formed. Forces separated. The quantum fields settled into their current values. But was the vacuum state we inhabit today the same as the vacuum state at the beginning of the universe? Interestingly, no. Physicists believe that the early universe underwent a period of rapid expansion, called inflation, driven by a quantum field in a high-energy vacuum state. This inflationary field was in a false vacuum, and when it decayed to a lower energy state, it released an enormous amount of energy that drove the expansion of space. In other words, the universe has already experienced at least one vacuum decay event. The decay of the inflationary field to a lower energy state is what gave rise to the hot Big Bang, the matter and radiation that eventually formed galaxies, stars, and planets. So, in a sense, vacuum decay is not just a theoretical possibility. It is part of the history of our universe. But the decay of the inflationary field was different from the vacuum decay we are discussing now. Inflation happened early, when the universe was tiny and uniform. The decay occurred everywhere at once, or nearly so, filling the universe with energy that became the matter and radiation we see today. If the Higgs field were to decay now, it would not happen everywhere at once. It would start in a single bubble and expand outward. And the universe inside the bubble would not be filled with matter and radiation. It would be a different vacuum state, with different laws of physics, incompatible with life. This distinction is important. The vacuum decay that might occur in our future is fundamentally different from the vacuum transitions that occurred in the past. Part 6. Philosophical Implications and the Meaning of Existence. What does it mean to live in a metastable universe? What does it say about the nature of existence? For some, the idea of vacuum decay is terrifying. It suggests that reality is fragile, that everything we know could end without warning, that there is no ultimate safety or permanence. For others, it is liberating. It reminds us that the universe is stranger and more mysterious than we often allow ourselves to believe. It suggests that existence itself is a kind of accident, a temporary configuration of fields and forces that need not have been this way. And for still others, it is irrelevant. If vacuum decay occurs, it happens at the speed of light. There is no suffering, no prolonged end, no awareness of what is happening. From the perspective of conscious beings, it would be instantaneous and painless. But I think there is something deeper here. Something about the nature of knowledge and uncertainty. We often seek certainty. We want to know that the world is stable, that the future is predictable, that we can plan and build and create without fear of fundamental disruption. But the universe does not owe us certainty. The laws of physics, for all their precision, are probabilistic at the quantum level. The future is not written. Anything that is not forbidden by those laws can, in principle, occur. Vacuum decay is a reminder that we live in a probabilistic universe where even the most unlikely events are possible. It is humbling, it is unsettling, but it is also, in a way, freeing. Because if the universe is not deterministic, if the future is not fixed, then we have agency. We have the ability to act, to choose, to create meaning in a cosmos that offers no guarantees. One of the goals of modern particle physics is to understand the vacuum, to determine whether it is truly stable, metastable, or unstable, to map the Higgs potential at all energy scales, to discover new particles and forces that might alter our understanding. The Large Hadron Collider, the world's most powerful particle accelerator, has been searching for signs of new physics beyond the standard model. So far, it has found none. The Higgs boson behaves exactly as the standard model predicts. No supersymmetric particles, no extra dimensions, no unexpected forces. But absence of evidence is not evidence of absence. The LHC can only probe energies up to a few tera-electron volts. The Planck scale is 15 orders of magnitude higher. There is an enormous range of energies we have not yet explored. Future experiments may reveal new physics. A new particle accelerator more powerful than the LHC could probe higher energies. Astrophysical observations, studying cosmic rays or gravitational waves, might provide indirect evidence of Planck-scale phenomena. Precision measurements of the Higgs and top quark masses, refining our estimates of the vacuum stability, could shift the calculations. Or we might find that the standard model is correct at all accessible energies, and that new physics only emerges at the Planck scale, forever beyond our reach. Either way, the question of vacuum stability remains one of the most profound in all of physics. It touches on the nature of reality itself. It asks whether the universe we inhabit is stable or temporary, eternal or contingent. And it reminds us that for all our knowledge, for all our technology, there are still mysteries at the heart of existence. Before we conclude, there is one more puzzle worth mentioning. It relates to the energy of the vacuum itself. Einstein's equations of general relativity include a term called the cosmological constant, which represents the energy density of empty space. For decades, physicists assumed this constant was zero, or very close to zero. But in the late 1990s, observations of distant supernovae revealed that the expansion of the universe is accelerating. Something is pushing galaxies apart, counteracting the pull of gravity. Physicists call this mysterious force dark energy, and the simplest explanation is that dark energy is the energy of the vacuum itself, the cosmological constant. The problem is, when physicists calculate what the vacuum energy should be based on quantum field theory, they get a number that is about 120 orders of magnitude larger than what we observe. This is called the cosmological constant problem, and it is one of the biggest unsolved mysteries in physics. Why is the vacuum energy so small? If quantum fields have zero-point energy, if virtual particles are constantly popping in and out of existence, why does empty space not have an enormous energy density? No one knows. And here is where it connects to vacuum decay. The vacuum energy, the cosmological constant, is related to the state of the quantum fields. If the Higgs field were in a different vacuum state, the cosmological constant would be different. Some physicists have speculated that the true vacuum, The lowest energy state the Higgs field could tunnel to might have a negative cosmological constant. If the universe transitioned to that state, space itself might collapse. Not just matter and atoms, but the very fabric of space-time could implode, creating a cosmic catastrophe beyond even vacuum decay. But this is speculation. We do not know the value of the cosmological constant in the true vacuum. We do not even know for certain that a true vacuum exists. What we do know is that the vacuum we currently inhabit has a small, positive cosmological constant, causing the universe to expand. And that expansion, interestingly, might protect us from vacuum decay. Here is an interesting twist. The expansion of the universe might reduce the likelihood of vacuum decay reaching us. As the universe expands, space itself stretches. Distant galaxies are moving away from us, not because they are traveling through space, but because the space between us and them is growing. This expansion is accelerating. Galaxies that are far enough away are receding faster than the speed of light, not because they are moving faster than light through space, but because the space itself is expanding faster than light can cross it. This creates a boundary called the cosmic event horizon. Beyond this horizon, galaxies are receding so fast that light from them will never reach us. They are effectively cut off from our observable universe. Now, imagine a bubble of true vacuum forming beyond the cosmic event horizon. It expands at the speed of light, but the space between the bubble and us is also expanding faster than light. The bubble would never catch up. It would never reach us. This means that vacuum decay events occurring in distant regions of the universe, beyond the event horizon, pose no threat to us. They are isolated by the expansion of space itself. But this protection is not absolute. If a bubble forms within our cosmic event horizon, it will eventually reach us. And as the universe continues to expand and accelerate, the event horizon moves outward, encompassing more and more space. So cosmic expansion provides some protection, but it is not a guarantee of safety. Here is a strange thought. If vacuum decay is possible, if bubbles of true vacuum can form and expand, why have we not seen evidence of it? The universe is vast. It has existed for nearly 14 billion years. If vacuum decay were occurring at a significant rate, we might expect to see signs of it. Regions of space where the laws of physics are different, boundaries between different vacuum states, anomalies in the cosmic microwave background or in the distribution of galaxies. But we see none of that. The universe appears uniform. The laws of physics seem to be the same everywhere we look. This could mean several things. It could mean that vacuum decay is extraordinarily rare, rarer than we currently estimate. It could mean that we are in a region of space where it has not occurred yet. Or it could mean that our calculations are wrong, and the vacuum is actually stable, not metastable. There is also a darker interpretation. If vacuum decay occurs, it propagates at the speed of light. Once a bubble forms, it swallows everything in its path. There would be no survivors, no remnants, no evidence left behind. If a civilization on the other side of the galaxy triggered vacuum decay through some experiment or accident, the bubble would expand outward, erasing stars and planets until it reached us, and we would see nothing until the instant it arrived. This is sometimes invoked as a possible solution to the Fermi paradox, the question of why we have not detected signs of intelligent alien civilizations. Perhaps advanced civilizations, in their quest to understand the universe, probe energies high enough to trigger vacuum decay. And once they do, they and everything around them are erased. But this is pure speculation. We have no evidence that vacuum decay has ever occurred anywhere in the observable universe. The fact that we exist suggests that it has not, at least not in our past light cone. So where does this leave us? We have a universe that might be metastable, a vacuum that could in principle decay at any moment, a cosmic threat that is silent, invisible, and unstoppable. And yet, here we are, living, thinking, creating. The probability of vacuum decay occurring in the next billion years is extraordinarily small. The lifetime of the false vacuum is estimated to be far longer than the current age of the universe. We are not in immediate danger. The sun will burn out long before vacuum decay becomes a concern. But the possibility exists, and that, in itself, is profound. It reminds us that the universe is not a static eternal backdrop. It is a dynamic evolving system, governed by quantum fields and probabilistic laws. The stability we perceive is not guaranteed. It is a consequence of the current state of those fields, a state that might not last forever. And it reminds us of the limits of our knowledge. We do not fully understand the vacuum. We do not know if new physics at the Planck scale stabilizes or destabilizes it. We do not know if there are other threats we have not yet imagined. But we continue to search. We build particle accelerators. We observe the cosmos. We refine our theories. We ask questions. Because that is what we do. We are curious. We seek to understand. And even if the universe is metastable, even if reality itself is temporary, the pursuit of knowledge is meaningful. Vacuum decay is not the only existential threat the universe poses. There are gamma-ray bursts, supernovae, asteroid impacts, rogue black holes, the eventual heat death of the universe. But vacuum decay is unique. It is not a localized event. It is not something we could detect or avoid. It is a fundamental instability in the fabric of reality itself. And yet, paradoxically, it is also one of the least urgent threats. The probability is so low, the timescales so vast, that it has no practical impact on our lives or civilization. So why discuss it? Why spend time contemplating something so unlikely and so beyond our control? Because it teaches us something important. It teaches us humility. It reminds us that the universe is not designed for our comfort or survival. It is indifferent. And the laws of physics, for all their elegance, do not guarantee permanence. But it also teaches us resilience, because despite the uncertainties, despite the cosmic threats, we are here. We exist. We thrive. We build civilizations, create art, explore the cosmos. The universe may be metastable, but that does not make our existence less meaningful. If anything, it makes it more precious. Because we are not guaranteed. We are contingent. We are temporary. And that is okay. Fear is a natural response to danger. It helps us survive. But fear of vacuum decay is different. It is not fear of something we can avoid or prepare for. It is fear of the unknown, the uncontrollable, the inevitable. And that kind of fear, if we let it, can paralyze us. But here is the thing. Vacuum decay, if it occurs, would be instantaneous from our perspective. No warning, no suffering, no prolonged end. It would be, in a very real sense, the gentlest apocalypse. One moment we exist, the next we do not. No pain, no terror, no awareness. Compare that to other cosmic threats. A nearby supernova could bathe the Earth in lethal radiation, causing mass extinctions over years or decades. An asteroid impact could trigger global climate change, starvation, and collapse. A rogue black hole could tear the solar system apart, flinging planets into the void. Vacuum decay, for all its fundamental strangeness, is at least quick. But I think the real lesson here is not about fear. It is about perspective. We live in a universe that is vast, ancient, and strange. The laws of physics that govern it are precise and mathematical, but they are also probabilistic and contingent. Nothing is guaranteed, nothing is eternal. And yet, here we are, conscious beings capable of contemplating our own existence, asking questions about the nature of reality, seeking meaning in a cosmos that offers none. That is extraordinary. Part 7. consciousness, time, and the arrow of existence. There is a philosophical question lurking beneath all of this. What does it mean to exist in a metastable universe? What does it mean for conscious beings like us to contemplate our own potential non-existence? Consciousness is a mystery. We do not fully understand how it arises, how subjective experience emerges from the physical processes in our brains. But we know that it exists. We are aware. We think. We feel. And if vacuum decay were to occur, consciousness would end. Not just individual consciousness, but the very possibility of consciousness. Because consciousness depends on complex structures, neurons firing, chemicals interacting, information processing, and all of that depends on the current laws of physics. Change the laws, and consciousness becomes impossible. This raises a strange question. If the universe decays to a true vacuum, if the laws of physics change such that consciousness cannot exist, does the universe still exist in any meaningful sense? This is not a scientific question. It is a philosophical one. But it is worth pondering. Some philosophers argue that existence without observers is meaningless, that the universe, in some sense, exists only insofar as it is observed. If consciousness ends, if there are no observers, does the universe still exist? Others argue that the universe is independent of observers, that it existed before consciousness emerged, and it would continue to exist in some form, even if consciousness disappeared. I do not have an answer, but I find the question fascinating because it touches on the deepest mysteries of existence. What does it mean to be? What is the relationship between matter and mind, between the physical universe and subjective experience? Vacuum decay, in its own strange way, forces us to confront these questions. Time is strange. We experience it as a flow, a progression from past to future. But in the equations of physics, time is symmetric. The laws work equally well forward and backward. So why does time seem to flow in one direction? Why do we remember the past but not the future? Why do we age? Why does entropy increase? Why does the universe evolve from order to disorder? This is called the arrow of time, and it is one of the great puzzles in physics. Vacuum decay, interestingly, is related to the arrow of time. The transition from false vacuum to true vacuum is an irreversible process. Once the bubble forms, it expands. It does not contract. The vacuum does not spontaneously tunnel back to the false state. This is because the true vacuum is lower in energy. The transition releases energy, and that energy drives the expansion. To reverse the process, to go from true vacuum back to false vacuum, would require adding energy. And in a universe governed by the second law of thermodynamics, processes that require energy input are unlikely. So vacuum decay, if it occurs, is a one-way process. It defines an arrow of time. But here is the deeper question. If the universe transitions to a true vacuum, if the laws of physics change, would time still flow? Would there still be an arrow? We do not know. The arrow of time, as we understand it, depends on the current laws of physics, on the behavior of entropy and energy. In a different vacuum state, with different laws, the arrow of time might not exist, or it might point in a different direction. This is speculation, but it illustrates how deeply vacuum decay challenges our understanding of reality. It is not just about the end of matter or the destruction of atoms. It is about the potential end of time itself. Let us return to the idea of the energy landscape, the mathematical space where the Higgs field can take different values and each value corresponds to a different energy. This landscape is not a physical place. It is an abstract, mathematical construct. But it is useful for visualizing the vacuum state. Imagine a vast, undulating terrain, with hills, valleys, and plains. Each point on this landscape represents a possible value of the Higgs field. The height at each point represents the energy of that configuration. Our universe corresponds to a particular point on this landscape, a valley, where the Higgs field has settled into a stable or metastable configuration. The question is this the deepest valley, or are there deeper valleys elsewhere? String theory, a theoretical framework that attempts to unify quantum mechanics and gravity, suggests that the energy landscape might be incredibly complex, not just a few valleys and hills, but a vast, multidimensional space with an enormous number of possible vacuum states. This is called the string theory landscape. In this picture, the universe we inhabit is just one of many possible configurations. Each configuration corresponds to a different vacuum state, with different laws of physics, different particle masses, different forces. Some of these configurations are stable, some are metastable, some are unstable and decay immediately. And we happen to find ourselves in a metastable configuration because it is one of the few that allows for the existence of observers. This is a controversial idea. Some physicists find it unsatisfying because it suggests that the laws of physics are not unique, that they are contingent on which vacuum state the universe happens to be in. Others find it elegant because it explains why the constants of nature are fine-tuned for life. We exist in this particular vacuum state because it is one of the rare configurations where observers can exist. But whether you find it satisfying or not, the string theory landscape raises profound questions about the nature of reality. Is our universe unique, or is it one of many? Is the vacuum state we inhabit special, or is it just one of countless possibilities in a vast mathematical space? Let us think about the far future, not the next 100 years or the next 1,000, but the next trillion years, the next 10 to the power of 100 years. If the vacuum does not decay, if it is stable or metastable with an extremely long lifetime, what happens to the universe? Current cosmological models suggest that the universe will continue to expand forever, driven by dark energy. Galaxies will drift apart. Stars will burn out. Black holes will evaporate through Hawking radiation. Eventually, the universe will reach a state of maximum entropy, a cold, dark, empty void where no complex structures can exist. This is called the heat death of the universe. But if the vacuum is metastable, there is another possibility. At some point, perhaps in the unimaginably distant future, a bubble of true vacuum will form. It will expand, consuming the dead, dark universe, rewriting the laws of physics. What would this mean? Would it be the end of the universe or a new beginning? We do not know. The true vacuum, by definition, is a lower energy state, but we do not know what it looks like. We do not know if matter could exist there, or if stars and galaxies could form. We do not know if consciousness could arise. It is possible that the true vacuum is a lifeless void, incompatible with complexity. Or it is possible that it is something entirely different, a new kind of universe with new laws, new particles, new possibilities. This is pure speculation, but it illustrates the strangeness of vacuum decay. It is not just the end of our universe, it is the potential beginning of something else. Part 8. Experimental Physics, Fewer Discoveries, and the Search for Answers. We have covered a lot of ground. We have explored the nature of the vacuum, the possibility of vacuum decay, the metastability of the Higgs field, the expansion of bubbles at the speed of light, the philosophical implications of living in a temporary universe. But now, let us ask a different question. What does all of this mean? For some, the idea of vacuum decay is nihilistic. It suggests that everything is temporary, that nothing matters, that we are all just fleeting configurations of particles in a universe that could end without warning. But I do not see it that way. Yes, the universe might be metastable. Yes, vacuum decay is possible. Yes, everything we know could end in an instant, but that does not make our existence meaningless. If anything, It makes it more meaningful, because meaning is not something the universe gives us. It is something we create. We find meaning in our relationships, in our work, in our pursuit of knowledge and beauty. We create meaning through our actions, our choices, our love. The universe does not care about us. It is indifferent, but we care about each other, and that is enough. Vacuum decay reminds us that we are not guaranteed, that existence is a gift, not a right, that the time we have, however long or short, is precious. And so we continue. We build. We explore. We ask questions. We seek to understand the universe, even if that understanding reveals uncomfortable truths, because that is what makes us human: our curiosity, our resilience, our ability to find meaning even in the face of uncertainty. There is something beautiful about physics: the elegance of the equations, the precision of the predictions, the way simple mathematical laws can describe the behavior of everything from subatomic particles to galaxies. And vacuum decay, for all its strangeness, is a consequence of those laws. It arises naturally from quantum field theory, from the properties of the Higgs field, from the mathematics of energy landscapes and tunneling. It is not an aberration. It is not a mistake. It is a feature of the universe we inhabit. And that, to me, is beautiful, because it shows that the universe is not arbitrary. It follows rules. And those rules, when you understand them deeply enough, reveal profound truths about the nature of reality. Vacuum decay is one of those truths. It is unsettling. It is strange. But it is also a reminder of how much we have learned, how far we have come in our understanding of the cosmos. 200 years ago, we did not know about atoms. 100 years ago, we did not know about quantum mechanics. 50 years ago, we did not know about the Higgs field. And now, we are contemplating the stability of the vacuum itself. We are asking whether the universe is eternal or temporary. We are probing the deepest levels of reality. That is progress. That is knowledge. That is the triumph of the human mind. One of the challenges of discussing vacuum decay is that it is easy to sensationalize, to make it sound like an imminent threat, a reason to panic, a cosmic catastrophe waiting to happen. But that is not the right way to think about it. Vacuum decay is a theoretical possibility based on our current understanding of particle physics. The probability is extraordinarily low. The timescales are unimaginably long. It is not something we need to worry about in any practical sense, but it is something we should understand, because it teaches us about the nature of the universe. It challenges our assumptions about stability and permanence. It reminds us that reality is stranger and more complex than we often imagine, and that is worth communicating. Not to frighten people, but to inspire them, to show them the beauty and depth of modern physics, to invite them to contemplate the profound mysteries of existence. Science communication is important, because science is not just a body of knowledge. It is a way of thinking, a way of asking questions, of seeking evidence, of challenging assumptions. And the more people understand science, the better equipped they are to navigate the world, to make informed decisions, to appreciate the cosmos we inhabit. Vacuum decay is a perfect example. It is strange, it is counterintuitive, it is deeply fascinating. And by discussing it openly and honestly, we can help people understand the nature of reality a little bit better. Everything we have discussed is based on theory, mathematical calculations, estimates of particle masses, and energy landscapes. But how do we test these ideas? How do we know if the vacuum is truly metastable? The answer is experimentation, precision measurements of the Higgs boson mass, the top quark mass, and other parameters of the Standard Model, searching for new particles and forces that might stabilize or destabilize the vacuum, probing higher and higher energies in particle accelerators. Each new experiment refines our understanding. Each new measurement shifts the calculations slightly. And with each refinement, we get closer to the truth. The Large Hadron Collider has already provided invaluable data. The discovery of the Higgs boson in 2012 was a monumental achievement. But the LHC is just the beginning. Future accelerators, if they are built, could probe even higher energies, revealing new physics that might change our understanding of vacuum stability. There are also astrophysical observations. Cosmic rays, high-energy particles from space, provide a natural particle accelerator, reaching energies far beyond what we can create in laboratories. By studying these cosmic rays, physicists can search for signs of new physics. And there are gravitational wave detectors, neutrino telescopes, dark matter experiments. Each of these probes a different aspect of the universe, and each has the potential to reveal something new. Science is an ongoing process. We do not have all the answers, but we are getting closer. And every new discovery, every new measurement brings us one step closer to understanding the true nature of the vacuum. I mentioned earlier the idea of a multiverse, a vast collection of universes with different vacuum states, different laws of physics. This is a controversial idea, but it is worth exploring. In the multiverse hypothesis, our universe is just one of many. Each universe corresponds to a different vacuum state, a different point in the energy landscape. Some universes are stable, some are metastable, some are unstable and decay immediately after forming. And we happen to inhabit a metastable universe, because it is one of the few types of universes where observers can exist long enough to ask questions about vacuum stability. This is an application of the anthropic principle, the idea that the universe must be compatible with the existence of observers. If the vacuum were highly unstable, if it decayed quickly, no galaxies, stars, or planets would form. No life would arise. No observers would exist to contemplate the question. So the fact that we exist, the fact that we are here to discuss vacuum decay, implies that the vacuum in our universe has been stable long enough for us to evolve. But it does not imply that it will remain stable forever. The multiverse hypothesis is appealing because it explains why the constants of nature seem fine-tuned for life. We do not live in a typical universe. We live in one of the rare universes where the vacuum state, the particle masses, the force strengths all happen to allow for complexity and life. But the multiverse is also controversial. Critics argue that it is untestable, that if other universes exist but are causally disconnected from ours, we can never observe them, and therefore the hypothesis is not scientific. Proponents respond that the multiverse is a natural consequence of certain theories, like string theory and inflationary cosmology, and that even if we cannot observe other universes directly, we can test the theories that predict them. I do not know who is right, but the multiverse hypothesis is an intriguing idea, and it offers a possible explanation for why our universe has the properties it does. Eternal inflation is a variant of the inflationary theory that I mentioned earlier. In this picture, the universe is constantly undergoing inflation in some regions, while in other regions, inflation ends and normal space forms. Each region where inflation ends becomes a separate universe, a bubble in a vast, eternally inflating multiverse. And each of these bubbles can have different vacuum states, different laws of physics. In eternal inflation, the multiverse is not a static collection of universes. It is a dynamic, ever-expanding structure, with new universes forming constantly. And here is where it connects to vacuum decay. In eternal inflation, vacuum transitions are common. Bubbles of different vacuum states form and expand, sometimes colliding with each other, creating complex patterns in the multiverse. Our universe, in this picture, is just one bubble among countless others. And the vacuum state we inhabit is just one of many possible states. Eternal inflation is speculative, but it is based on well-understood physics, and it offers a compelling explanation for the structure and properties of the universe. And it suggests that vacuum decay far from being a rare and catastrophic event, might be a common occurrence in the multiverse. It is just that we happen to inhabit a bubble where it has not occurred yet. Here is a strange thought. What if our universe is a simulation, a computational model running on some advanced computer? The simulation hypothesis is popular in certain circles, partly because it seems to explain some of the strange features of quantum mechanics, the probabilistic nature of quantum events, the discrete nature of energy levels, the finite speed of light. All of these could be features of a simulated reality. And if our universe is a simulation, then vacuum decay takes on a different character. It would not be a fundamental instability in the fabric of reality. It would be a bug, a glitch, a failure mode in the simulation. Or, perhaps, it would be a planned event, a reset, a transition to a new version of the simulation with different parameters. I do not seriously advocate for the simulation hypothesis. There is no evidence for it, and it raises more questions than it answers. If we are in a simulation, who created it? What is the nature of the reality outside the simulation? And how would we ever know? But it is an interesting thought experiment, because it reminds us that our understanding of reality is always provisional. We build models, we test them, we refine them, but we can never be certain that we have the final answer. Vacuum decay is a consequence of our current best models of physics, but those models might be wrong, or incomplete, or part of a larger framework we have not yet discovered. And that is okay, because science is not about certainty. It is about asking questions and seeking answers, always open to the possibility that we might be wrong. Mathematics is the language of physics. Every law, every equation, every prediction is expressed in mathematical terms, and vacuum decay is no exception. The calculations that determine whether the Higgs field is in a stable, metastable, or unstable state involved advanced mathematics, differential equations, variational calculus, functional integrals, path integrals. These are not simple concepts. They require years of study to master, but they are incredibly powerful. They allow physicists to make precise predictions about the behavior of quantum fields, the stability of the vacuum, the properties of particles. And the beauty of mathematics is that it is universal. The equations that describe the Higgs potential are the same in London as they are in Tokyo, the same today as they were 1 billion years ago, the same on Earth as they would be in a distant galaxy. Mathematics transcends culture, language, and time. It is a tool for understanding the universe, and it has led to some of the most profound discoveries in human history. Vacuum decay is a mathematical consequence of quantum field theory. It arises from the equations, not from intuition or guesswork, and that is what makes it so compelling. It is not a wild speculation. It is a rigorous, calculated possibility. Of course, mathematics is only as good as the models we use. If our models are wrong, the predictions are wrong. But the process of mathematical reasoning, the rigor and precision it demands, is invaluable. It forces us to think clearly, to test our assumptions, to follow the logic wherever it leads, even if the conclusions are strange or unsettling. The universe is vast, but is it infinite? This is one of the great unanswered questions in cosmology. The observable universe, the part we can see, is finite. It has a radius of about 46 billion light-years. But beyond the observable universe, space might extend infinitely in all directions. If the universe is infinite, then vacuum decay takes on a different character. In an infinite universe, with infinite space and infinite time, even the most unlikely events become not just possible, but inevitable. If the probability of vacuum decay forming in a given volume of space in a given time is non-zero, no matter how small, then in an infinite universe, it will happen. An infinite number of times, in fact. But the bubbles would be separated by vast distances. If the universe is infinite and roughly uniform, Then bubbles of true vacuum could be forming constantly, scattered throughout space, each one expanding and consuming its local region. We would not see them unless one formed close enough to reach us, and given the vast scales involved, the probability of a bubble forming nearby is extraordinarily small. So, an infinite universe does not change the threat of vacuum decay. It just means that somewhere, in the infinite expanse, it might already be happening. But this is speculation. We do not know if the universe is infinite, and if it is, we have no way of observing the regions beyond our cosmic horizon. Still, it is an interesting thought, because it illustrates the power of infinity. In an infinite universe, everything that can happen does happen, somewhere. So when? There are things we can never know, not because we lack the technology or the intelligence, but because the universe itself imposes limits on knowledge. The speed of light is one such limit. Information cannot travel faster than light. This means there are regions of the universe we can never observe, events we can never detect, because the light from those regions will never reach us. The cosmic event horizon, which I mentioned earlier, is a boundary beyond which galaxies are receding faster than light. We can never receive signals from beyond that horizon. We can never know what is happening there. This is a fundamental limitation, not a temporary one, but a permanent feature of the universe. And it has implications for vacuum decay. If a bubble of true vacuum forms beyond the cosmic event horizon, we will never know about it. It will expand, consuming distant galaxies, but it will never reach us because the space between us and the bubble is expanding faster than the bubble can travel. In a sense, we are protected by ignorance. There could be countless bubbles of true vacuum forming in the distant universe, and we would never see them, never know they exist. But if a bubble forms close enough, within our cosmic horizon, it will eventually reach us, and there is nothing we can do to prevent it. This is the nature of the universe. It is vast, it is strange, and it imposes limits on what we can know and what we can control. Part 9. The Psychology of Uncertainty and the Value of Curiosity. Throughout this exploration, we have delved into some of the deepest and strangest ideas in modern physics: vacuum decay, metastability, quantum tunneling, the nature of the vacuum, the limits of knowledge. And you might be wondering, why bother? Why spend time contemplating something so unlikely, so distant, so beyond our control? The answer is curiosity. Curiosity is what drives us to ask questions, to seek understanding, to explore the unknown. It is one of the most fundamental human traits, and it has led to every major discovery in history. We went to the moon because we were curious about what was there. We build particle accelerators because we are curious about the fundamental nature of matter. We study the stars because we are curious about the universe. And we contemplate vacuum decay because we are curious about the stability of reality itself. Curiosity is not always practical. It does not always lead to immediate benefits. But it enriches our lives. It expands our understanding. It connects us to the cosmos in a profound way. And sometimes curiosity leads to unexpected discoveries. Quantum mechanics was developed out of pure curiosity, and it led to the invention of semiconductors, lasers, and computers. General relativity was a theoretical exercise, and it is now essential for GPS technology. We never know where curiosity will lead, but the journey itself is worthwhile. Wonder is closely related to curiosity, but it is deeper. Wonder is the feeling we get when we confront something vast, something beautiful, something beyond our full comprehension. The night sky inspires wonder. The complexity of a living cell inspires wonder. The elegance of the equations that describe the universe inspires wonder. And vacuum decay, for all its strangeness, inspires wonder, because it reveals that the universe is not what it seems, that the stability we perceive is not guaranteed, that reality itself is stranger and more mysterious than we imagined. Wonder is valuable. It reminds us that we are small, that we are part of something much larger, that there are mysteries we have only begun to explore. And wonder drives us to learn more, to ask deeper questions, to push the boundaries of knowledge. So when we contemplate vacuum decay, we are not just engaging in abstract speculation, we are experiencing wonder. We are confronting the profound strangeness of existence, and that is meaningful. When we understand the universe, when we grasp the laws of physics, we gain power, the power to manipulate matter, to harness energy, to shape the world. But we also gain responsibility, the responsibility to use that power wisely, to consider the consequences of our actions, to avoid causing harm. Vacuum decay, interestingly, is one area where human action might, in principle, have an impact. If we were to create extremely high energy densities, perhaps in a future particle accelerator far more powerful than the LHC, we might, in theory, increase the probability of triggering vacuum decay. This is purely hypothetical. Current accelerators are nowhere near the energies required, and the probability is so low that even the most extreme experiments imaginable would not pose a significant risk. But it raises an interesting ethical question. If we had the technology to probe energies near the Planck scale, energies where vacuum decay becomes more likely, should we do it? On one hand, the pursuit of knowledge is valuable. Understanding the universe at its deepest levels could lead to transformative discoveries. On the other hand, if there is even a tiny risk of triggering an event that could end the universe, is it worth it? I do not have an answer, but it is a question worth contemplating, because as our technology advances, as we push the boundaries of what is possible, we will face more and more such dilemmas. And we need to be thoughtful. We need to consider not just what we can do, but what we should do. Humility is an underrated virtue. In a world that celebrates confidence and certainty, humility reminds us of our limitations. We do not know everything. Our models are imperfect. Our understanding is incomplete. Vacuum decay is a reminder of this. We calculate that the vacuum might be metastable, but we do not know for certain. We estimate the lifetime of the false vacuum, but our estimates depend on parameters we have not measured precisely. And there could be new physics, undiscovered forces, particles we have not yet detected that change everything. Humility means accepting that we might be wrong, that our current understanding is provisional, that the universe might surprise us. And that is okay, because science is not about having all the answers. It is about asking the right questions and being open to new evidence. Humility also means respecting the universe, recognizing that it is vast, ancient, and complex, that it does not owe us stability or comfort or permanence. And in that recognition, there is a kind of peace. Because if we accept that the universe is indifferent, that it follows its own laws regardless of our wishes, then we can stop demanding certainty and start embracing the mystery. At the end of the day, the deepest question is not about vacuum decay or the stability of the Higgs field. The deepest question is, why is there something rather than nothing? Why does the universe exist? Why are there quantum fields, particles, forces, space, time? Why does anything exist at all? This is a question that physics cannot answer. It is a question beyond science, beyond mathematics, beyond logic for answers. Others accept the question as unanswerable and focus on understanding the universe that does exist. But the question lingers. And vacuum decay, in its own way, touches on it. Because vacuum decay is about the nature of existence itself. It asks whether the universe is stable or temporary. It asks whether reality is permanent or contingent. And in asking these questions, it reminds us of the profound mystery at the heart of everything. We are here. We exist. We are conscious aware, capable of contemplating the cosmos. And that is extraordinary. Whether the vacuum is stable or metastable, whether the universe lasts forever or ends in an instant, the fact that we are here, now, experiencing this moment, is a wonder. Part 10. Final reflections on reality, impermanence, and wonder. Let us delve deeper into what physicists mean when they talk about the quantum vacuum. This is worth exploring in detail because it fundamentally challenges our intuition about reality. In classical physics, a vacuum was simple. It was the absence of matter. Remove all the air from a container and you have a vacuum. Remove all particles, all atoms, all molecules, and you have perfect emptiness. Nothing. But quantum mechanics changed everything. In quantum field theory, the framework that describes particles and forces at the smallest scales, there is no such thing as true emptiness. Every point in space, every cubic centimeter of the universe is filled with quantum fields. These fields are fundamental. They are not made of anything more basic. They simply exist. The electromagnetic field exists everywhere. So does the electron field, the quark fields, the Higgs field, the gravitational field. All of them overlapping, occupying the same space, each vibrating with its own characteristic frequency. And these fields have energy even when they are at their lowest state, their ground state. This is not optional. It is a consequence of the uncertainty principle, one of the foundational principles of quantum mechanics. The uncertainty principle states that you cannot know both the position and momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. This is not a limitation of measurement. It is a fundamental property of reality. Applied to fields, the uncertainty principle means that a field cannot be perfectly still. It cannot have exactly zero energy. There must always be fluctuations, vibrations, uncertainty. These fluctuations manifest as virtual particles, particle-antiparticle pairs that pop into existence for incredibly brief moments, then annihilate. An electron and a positron appear from nothing, exist for a tiny fraction of a second, then disappear. A photon materializes, then vanishes. These virtual particles borrow energy from the vacuum itself, permitted by quantum mechanics as long as they pay it back quickly enough that the universe does not notice. This might sound like mathematical fiction, but it is not. Virtual particles have real, measurable effects. They alter the energy levels of atoms in ways that can be detected with extraordinary precision. They affect how light propagates through space. They create forces between objects. The Casimir effect is perhaps the most striking demonstration. Place two uncharged metal plates very close together in a vacuum. Classical physics predicts nothing should happen. But quantum mechanics predicts that the plates will attract each other, pulled together by the pressure of virtual particles. Why? Because the space between the plates is so narrow that only virtual particles with certain wavelengths can exist there. Outside the plates, in the wider expanse of space, virtual particles of all wavelengths can exist. This creates a difference in pressure. More virtual particles push on the outside of the plates than push on the inside, and so the plates attract. This has been measured. The effect is real. Virtual particles are real, in the sense that they have real consequences. So when we talk about a vacuum, we are not talking about nothingness. We are talking about a seething ocean of quantum fields and virtual particles, a complex dynamic system that only appears empty because we cannot see the fluctuations directly. And this is the vacuum that might be metastable. This is the foundation of reality that could, in principle, transition to a different state. The Higgs field deserves special attention because it is central to the question of vacuum stability. Let me explain it more thoroughly. Most quantum fields have a vacuum expectation value of 0. That means in their ground state, when no particles are present, The field itself has zero intensity. It is there, but it is turned off, so to speak. The Higgs field is different. It has a non-zero vacuum expectation value. Even in empty space, even when no Higgs bosons are present, the Higgs field has an intensity of about 246 gigaelectron volts. This is not a small number. It is a fundamental property of our universe. Why does this matter? Because particles acquire mass by interacting with the Higgs field. The stronger the interaction, the more mass the particle has. Electrons interact weakly with the Higgs field, so they have a small mass. Top quarks interact strongly, so they have a large mass. Photons do not interact with the Higgs field at all, so they are massless. This mechanism, called the Higgs mechanism, is how the universe generates mass. Without the Higgs field, electrons, quarks, and other particles would be massless. They would travel at the speed of light, unable to bind together into atoms. Chemistry would not exist. Complexity would not be possible. The universe would be a very different place. Now, the Higgs field, like all quantum fields, has a potential energy. This potential describes how the energy of the field changes as its intensity changes. And the shape of this potential is critical. Imagine a graph. The horizontal axis represents the intensity of the Higgs field. The vertical axis represents the potential energy. The shape of this graph determines the behavior of the field. In our universe, the Higgs field sits at an intensity of about 246 gigaelectron volts. This corresponds to a minimum in the potential energy curve. The field has settled there because it is a stable or metastable equilibrium. But here is the question. Is this the absolute minimum, or is there a deeper minimum at a different field intensity? Calculations based on the measured mass of the Higgs boson and the top quark suggest that at very high field intensities, far higher than the current value, the potential energy curve dips down. It develops a second minimum, much deeper than the first. This means the Higgs field in our universe is in a local minimum, not the global minimum. It is like a ball in a valley, but not the deepest valley. It is metastable. Now, why has the field not already transitioned to the deeper minimum? Because there is an energy barrier separating the two minima. To transition, the field would have to climb over a hill in the potential energy curve, and it does not have enough energy to do that. But quantum mechanics offers another possibility. Quantum tunneling. The field could tunnel through the barrier, jumping from the false vacuum to the true vacuum without ever having enough energy to climb over the hill. This is possible, but extraordinarily unlikely. The barrier is enormous, corresponding to energies near the Planck scale. Tunneling through such a barrier is a rare event, so rare that it might not happen for timescales far longer than the current age of the universe. But it is not impossible, and that is what makes vacuum decay a real, if remote, possibility. The top quark plays a crucial role in determining the stability of the Higgs potential. Let me explain why. The top quark is the heaviest known fundamental particle. It has a mass of about 173 gigaelectron volts, which is roughly the mass of a gold atom, but concentrated into a single elementary particle. This is extraordinarily heavy for a fundamental particle. The top quark interacts very strongly with the Higgs field. In fact, its interaction is so strong that it significantly affects the shape of the Higgs potential at high energies. Here is how it works. Quantum fields do not exist in isolation. They interact with each other. Virtual particles from one field can affect the behavior of another field. These interactions are described mathematically using a framework called renormalization group equations. When physicists calculate how the Higgs potential changes at higher and higher energies, they find that the top quark interaction drives the potential downward at very high field intensities. The strong coupling between the top quark and the Higgs field creates a negative contribution to the potential energy. If the top quark were lighter, this effect would be weaker, and the Higgs potential might remain positive at all energies. indicating a stable vacuum. If the top quark were heavier, the effect would be stronger, and the vacuum might be unstable, decaying rapidly. But the top quark has just the right mass to make the vacuum metastable. Not stable, not unstable, but balanced on the edge. This is remarkable. A tiny change in the top quark mass, just a few giga-electron volts, could shift the vacuum from stable to unstable, or vice versa. The universe we inhabit is incredibly sensitive to the properties of fundamental particles, and this sensitivity raises deep questions. Why does the top quark have the mass it does? Why is the universe metastable rather than stable or unstable? Is this a coincidence, or is there a deeper explanation? Some physicists invoke the anthropic principle, arguing that we exist in a universe with these particular properties because they allow for complexity and life. Others search for new physics, new particles or forces that might explain why the constants of nature have the values they do. But as of now, we do not have a complete answer. We only have measurements and calculations that suggest the vacuum is metastable, poised in a delicate balance. To truly understand vacuum stability, we need to delve a bit deeper into quantum field theory. Bear with me. This is technical, but it is the foundation of everything we have discussed. Quantum field theory is the framework that combines quantum mechanics and special relativity. It describes particles not as solid objects, but as excitations in underlying quantum fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. These fields interact with each other through processes involving virtual particles. For instance, an electron can emit a virtual photon, which is then absorbed by another electron. This interaction creates the electromagnetic force between the two electrons. But when you calculate the effects of these interactions, you encounter infinities. The mathematics predicts that certain quantities, like the mass or charge of a particle, should be infinite. This is clearly wrong, since we can measure these quantities and they are finite. The solution is a process called renormalization. You absorb the infinities into the definitions of the fundamental parameters, like mass and charge. You use the measured values of these parameters rather than trying to calculate them from first principles. Renormalization is subtle and often misunderstood, but it works. It allows physicists to make extraordinarily precise predictions. Quantum electrodynamics, the quantum field theory of light and matter, is the most precisely tested theory in all of science. Its predictions agree with experiments to better than 1 part in a billion. Now, renormalization also affects the Higgs potential. As you probe higher and higher energies, the interactions between the Higgs field and other fields change. The potential energy curve shifts. What looks like a stable minimum at low energies might not be a minimum at high energies. This is why physicists calculate the running of the Higgs potential. They use renormalization group equations to determine how the potential changes as you move to higher energy scales. And this is how they discovered that the vacuum might be metastable. At low energies, the energies we experience in everyday life, the Higgs field sits in a stable minimum. But at energies near the Planck scale, the potential dips down, creating a second, deeper minimum. The vacuum we inhabit is only a local minimum, not the global one. This is a profound insight. It suggests that the laws of physics, which seem eternal and unchanging, are actually contingent on the energy scale. At different energies, the universe behaves differently, and it raises the possibility that our universe, stable as it seems, is not in its lowest energy state. The Planck scale represents the frontier of our understanding. It is the energy scale where quantum mechanics and general relativity, the two pillars of modern physics, come into conflict. General relativity describes gravity as the curvature of space-time. Massive objects bend space around them, and this curvature is what we experience as gravitational attraction. The theory is extraordinarily successful. It explains the motion of planets, the bending of light around stars, the expansion of the universe, the existence of black holes. But general relativity is a classical theory. It does not incorporate quantum mechanics, and at very small scales, quantum effects become important. Space-time itself should fluctuate, just like quantum fields do. But general relativity does not account for this. Quantum mechanics, on the other hand, describes the behavior of particles and fields at the smallest scales. It is probabilistic, indeterministic, and extraordinarily successful at predicting the behavior of atoms, molecules, and subatomic particles. But quantum mechanics does not include gravity. The gravitational force is so weak compared to the other forces that it can usually be ignored at the quantum level. But at the Planck scale, gravity becomes as strong as the other forces, and it can no longer be ignored. The Planck energy is about 10 to the 19th gigaelectron volts. This is the energy at which quantum fluctuations of spacetime become significant. The Planck length is about 10 to the negative 35 meters. This is the scale at which space-time becomes grainy, foamy, uncertain. At the Planck scale, our current theories break down. We need a theory of quantum gravity, a framework that unifies quantum mechanics and general relativity. But we do not have one. Not yet. String theory is one candidate. It proposes that particles are not point-like objects, but tiny, vibrating strings. The vibrations of these strings give rise to different particles. And in string theory, gravity emerges naturally as one of the vibrational modes. Loop quantum gravity is another candidate. It proposes that space-time itself is quantized, made up of discrete loops and nodes, rather than being smooth and continuous. But both string theory and loop quantum gravity are still incomplete. They make predictions that are difficult or impossible to test with current technology. And so the question of what happens at the Planck scale remains open. This uncertainty affects our understanding of vacuum stability. The calculations that suggest the vacuum is metastable depend on extrapolating the laws of physics up to the Planck scale. But if there is new physics at those energies, if string theory or some other framework changes the rules, the conclusions could be different. Maybe the vacuum is actually stable, and the calculations are missing something. Maybe it is more unstable than we think. We simply do not know, and that is okay. Science is a process. We build models, we test them, we refine them. We do not have all the answers, but we keep searching. String theory, if it is correct, offers a radically different picture of the universe. Instead of a single vacuum state, string theory predicts an enormous number of possible vacuum states, perhaps 10 to the power of 500 or more. This vast collection of possible states is called the string theory landscape. Each state corresponds to a different configuration of the extra dimensions that string theory requires. And each configuration gives rise to different laws of physics, different particle masses, different force strengths. In this picture, our universe is just one point in the landscape, one particular configuration of extra dimensions that happens to give rise to the particles and forces we observe. But there are countless other configurations, other possible universes, with different laws. Some might have stable vacuums, some might have unstable vacuums, some might be incompatible with life. And the question is, why do we find ourselves in this particular configuration? Why does our universe have the properties it does? The anthropic principle offers one answer. We exist in this universe because it is one of the few configurations that allows for complexity. Stars, planets, and life. If the vacuum were unstable, if it had decayed long ago, we would not be here to ask the question. But this raises further questions. If the landscape is real, are all these other universes real too? Do they exist somewhere in some sense? Or are they just mathematical possibilities? We do not know. The landscape is a prediction of string theory, but string theory itself is not yet confirmed. We have no direct evidence for extra dimensions, or for the other vacuum states the theory predicts. But the landscape is an intriguing idea. It suggests that the universe we inhabit is not unique, that the laws of physics are not fundamental, that reality itself is more varied and strange than we imagined. And it offers a possible explanation for why the vacuum is metastable. If there are countless possible vacuum states, and we happen to inhabit one that is metastable, that is not surprising. It is simply a consequence of existing in a universe where the vacuum has not yet decayed. Let us think about the long-term future of the universe, assuming vacuum decay does not occur. What happens to stars, galaxies, and the large-scale structure of the cosmos? Stars burn by fusing hydrogen into helium in their cores. This releases energy, which we see as starlight. But stars do not last forever. They run out of fuel. Small stars, like red dwarfs, burn slowly and can last for trillions of years. But even they will eventually exhaust their hydrogen and fade away, becoming cold, dark remnants. Larger stars burn faster. A star like the Sun will last about 10 billion years. It is currently about 4.5 billion years old, so it has about 5.5 billion years left. When it runs out of hydrogen, it will expand into a red giant, swallowing the inner planets, possibly including Earth. Then it will shed its outer layers and collapse into a white dwarf, a dense, slowly cooling ember. The most massive stars burn even faster, lasting only a few million years. They end their lives in spectacular supernova explosions, leaving behind neutron stars or black holes. Over time, as stars die and new ones form from the remaining gas and dust, the universe will gradually run out of material for star formation. Galaxies will darken. The era of stars, the era we currently live in, will end. This will take a very long time, trillions of years, but it is inevitable, given the laws of physics. After the stars fade, galaxies will be populated by dark remnants, white dwarfs, neutron stars, black holes. These objects will orbit each other, occasionally colliding, merging, releasing gravitational waves. Eventually, even these remnants will evaporate. White dwarfs will cool to near absolute zero. Black holes will evaporate through Hawking radiation, a quantum process that slowly converts mass into radiation. This takes an unimaginably long time. A black hole with the mass of the Sun would take about 10 to the power of 67 years to evaporate. A supermassive black hole could last for 10 to the power of 100 years or more. But eventually, they too will disappear, and the universe will be left with nothing but a thin soup of particles, photons and neutrinos spread across an ever-expanding space. This is the heat death of the universe, a state of maximum entropy, where no complex structures can exist, where no energy gradients remain to drive processes. It is a bleak picture, but it is the far future, so far beyond anything we can directly concern ourselves with that it is almost abstract. And yet, vacuum decay offers an alternative ending. If the Higgs field transitions to the true vacuum before the heat death occurs, the universe would not fade slowly into darkness. It would transform suddenly, catastrophically, into something entirely different. Which fate awaits the universe? We do not know. Both are possibilities. Both are consequences of the laws of physics as we currently understand them. Here is a strange thought. If the universe reaches the heat death, if it becomes a cold, dark, empty expanse, could it be revived? Some physicists have speculated about quantum fluctuations in the far future. Given enough time, an enormous amount of time, quantum mechanics predicts that even the most unlikely events can occur. A fluctuation could, in principle, create a region of lower entropy, a pocket of order in the vast sea of disorder. This region could grow, forming a new universe, a new beginning. This is called a Boltzmann brane scenario, named after the physicist Ludwig Boltzmann. The idea is that in an infinite future, Random fluctuations could spontaneously create conscious observers, or even entire universes. They depend on assumptions about the nature of time, entropy, and quantum mechanics in the far future, and they raise more questions than they answer. Would a Boltzmann brain be truly conscious? Would a universe created by a quantum fluctuation have the same laws of physics as ours? Could such events really occur, or are they just mathematical curiosities? We do not know. The far future of the universe is a vast unknown, a frontier of speculation and imagination. But vacuum decay, interestingly, would prevent these scenarios from occurring. If the vacuum transitions to a true vacuum, if the laws of physics change, there would be no heat death, no slow fade, no quantum fluctuations creating new universes. There would only be the new vacuum with its own laws, its own properties, its own destiny. Matter and the vacuum are not separate. They are intimately connected, two aspects of the same underlying reality. Matter is made of particles, electrons, quarks, photons, and particles are excitations in quantum fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. These fields exist everywhere, permeating all of space. The vacuum is simply the state where these fields have their lowest energy, where no ripples, no particles are present. But the vacuum is not passive. It affects the behavior of particles. Virtual particles from the vacuum can interact with real particles, altering their properties. For instance, the mass of an electron is not a fixed, unchanging number. It is affected by interactions with virtual particles from the vacuum. The electron is constantly emitting and reabsorbing virtual photons, and this process contributes to its mass. This is called self-energy, and it is a fundamental aspect of quantum field theory. Every particle is influenced by the vacuum, shaped by the quantum fields around it. So when we talk about vacuum decay, we are talking about a transformation of the very foundation of matter. If the vacuum changes, the properties of particles change. Masses shift, forces strengthen or weaken. The chemistry of atoms alters. In the most extreme scenarios, atoms might not be stable. Protons could decay. Electrons could unbind from nuclei. Matter, as we know it, could cease to exist. This is why vacuum decay is so profound. It is not just the destruction of matter. It is the transformation of the laws that govern matter. It is a fundamental restructuring of reality itself. And yet, from another perspective, it is just a phase transition, like water freezing into ice or steam condensing into water. A change of state, from false vacuum to true vacuum. The universe would continue to exist. Space, time, quantum fields would still be there, but they would be arranged differently, governed by different rules. What would that new universe be like? We do not know. We cannot know. Because the laws of physics would be different. Our ability to predict or imagine would be limited. It is the ultimate unknown. Living in a metastable universe raises ethical questions, not in a practical sense, because there is nothing we can do about vacuum decay, but in a philosophical sense. If the universe could end at any moment, without warning, does that change how we should live? Does it affect our values, our priorities, our sense of meaning? Some might argue that it makes life more precious. If existence is temporary, if there are no guarantees, then every moment becomes valuable. Every experience, every relationship, every achievement matters more because it is fleeting. Others might argue that it makes life less meaningful. If everything could be erased in an instant, if our accomplishments, our civilizations, our legacies could disappear without a trace, then why bother? Why strive? Why build? Why create? I find the first perspective more compelling. Meaning is not derived from permanence. It is derived from experience, from connection, from the act of living itself. A beautiful sunset is not less beautiful because it lasts only a few minutes. A piece of music is not less moving because it ends. A life is not less meaningful because it is finite. And the same applies to the universe. If it is temporary, if it could end, that does not diminish its value. It enhances it. We are here, now, in this moment. We are conscious, we are aware, we can think, feel, create, love. And that is extraordinary, regardless of how long it lasts. Vacuum decay, in this sense, is a reminder to appreciate what we have, not to take existence for granted. Not to assume that the universe owes us stability or permanence, but to recognize that we are part of something vast and strange and wonderful, and to make the most of the time we have. We have traveled a long way together, from the nature of empty space to the Higgs field, from quantum tunneling to vacuum decay, from the speed of light to the limits of knowledge. We have explored the science, the mathematics, the philosophy. We have confronted unsettling ideas and found wonder in the strangeness of reality. And now, as we come to the end of this journey, let me leave you with a few final thoughts. First, the universe is not what it seems. The stability we perceive, the solidity of matter, the permanence of the laws of physics, all of these are contingent. They depend on the current state of quantum fields, a state that might not be eternal. Second, ignorance is not bliss. Understanding vacuum decay, grasping the metastability of the universe, does not make life more frightening. It makes it more profound. It deepens our appreciation for the cosmos and our place in it. Third, we are part of something extraordinary. We are configurations of atoms, assembled through billions of years of cosmic evolution, capable of contemplating the very foundations of reality. That is remarkable. That is meaningful. And fourth, the pursuit of knowledge is worthwhile, even if the universe is metastable, even if reality itself is temporary. The act of seeking to understand, of asking questions, of pushing the boundaries of human knowledge, that is valuable in itself. So the next time you look up at the night sky, remember what you have learned. The stars you see are made of atoms, held together by the current laws of physics. The space between them is filled with quantum fields, humming with zero-point energy. And the vacuum, the very fabric of reality, might be metastable, poised in a temporary equilibrium. And yet, here we are, alive, conscious, aware. That is the real wonder. Not that the universe might end, but that it exists at all, and that we are here to witness it. Thank you for joining me on this journey into the depths of physics. If you found this exploration meaningful, if you want to continue contemplating the mysteries of existence, consider liking this video and subscribing. There are so many more wonders to discover together. Until next time, stay curious, stay thoughtful, and remember that we live in a universe stranger and more beautiful than we often dare to imagine.